the momentum unit, okay? So first let's try and identify what exactly is momentum. Okay, to put it simply, momentum is the quantity that defines how difficult an object is to change the state of motion, okay? So something with a lot of momentum, it will be very difficult for you to change how it's moving. It's very difficult for you to change the direction, very difficult for you to stop its moving. Momentum is a vector quantity. Now that is in contrast to energy, or kinetic energy, which is a scalar quantity, okay? So momentum, being a vector quantity, exists in a particular direction, all right? If my marker is being thrown this way to the right of the room, that means that the marker has a net momentum to the right. Momentum, represented by the lowercase p, equals mv. And we understand here that momentum is a vector because it is a constant, mass, multiplied by a vector, velocity. Important to our understanding of momentum is the law of conservation of momentum. Conservation of momentum states that in any collision, in any interaction within a closed system, the momentum of all participants in the system, the total momentum of the system, cannot change, okay? So, for example, if I have this clip and this marker, or rather let me get two markers so you can see this more accurately. If I have two markers, this black marker is moving to the right at, let's say, 2 meters per second, and this red marker is moving to the left at 2 meters per second. So they both have the same magnitude of their velocity, but their velocity vectors are opposite, and you can see they're the same marker, so they have the same mass. So if we take the momentum of this marker and we calculate that, let's say this marker weighs 0.1 kilogram, therefore its momentum is 0.2 in the rightward direction. This marker will also have a momentum of 0.2, but in the leftward direction. Therefore, the net momentum, the total momentum of the system, is 0, because you got a positive 0.2 and you got a negative 0.2. The two cancel. Our momentum of the whole system will be 0. Therefore, if these two are moving and they collide, they might stick together. They might stop moving altogether, okay? And that is in agreement with our law of conservation of momentum. Because in before, our total momentum was 0, and now our total momentum is still 0 because they're not moving at all now, okay? So an interaction can happen, a collision can happen, but the total momentum of the system must remain constant, must not change. So we say that the sum of all the component momentums of the system must be a constant, therefore the change in momentum must be 0 for a closed system. So like we had in the energy unit, we had the work energy theorem. Here in the momentum unit, we have the impulse momentum unit, stating that the change in momentum of any single participant of the system is equal to the impulse on the system, which is equal to the integral from time A to time B of force as a function of time dt. Okay? Now notice here, this is not a dot product. Okay? This is just a simple multiplication of our force as a function of time multiplied by our time differential. Okay? So therefore, if we represent this as a force of, a force versus time curve, you could say that the impulse, J, is equal to the area under the curve of this force versus time curve. This area right here, which is what this integral is analyzing, okay? No, I'm sorry, it would be force on the y-axis and time on the x-axis would produce that, okay? So let's try and understand what that means conceptually, all right? Let's say I throw one of these markers at my whiteboard, okay? If I throw it, the marker has a mass and it has a velocity. Therefore, the marker will hurtle towards the whiteboard with some momentum, okay? And when it collides with the whiteboard will exert a normal force back onto the marker, okay? So the whiteboard, since it is exerting a force on the marker, is applying an impulse to the marker, okay? And we understand that the time during which this impulse is occurring is very short, because the the wall isn't going to stick to the marker for very long. The marker is going to collide, it's going to apply its force, and then the marker will fall back to the ground because all of its momentum has been opposed by the added impulse to the system. Okay? Impulse is a vector, okay, because force is a vector. All right? The reason work is not a vector is because of our dot product. Dot product converts vectors into scalars. All right? Since there is no dot product here, our resultant, the j, is going to be a vector. Okay? So whatever momentum that my marker had going into the wall, the resultant impulse, the resultant change in momentum, is going to be out of the wall. It's going to oppose the motion of the marker, such that the added impulse from the wall combined with the original momentum of the marker will eventually sum to zero. Okay, therefore the total momentum of the system will be reduced to zero. But wait a minute, Meek, you just told me about the law of conservation of momentum. How could the system's momentum be reduced to zero by the wall? And you'd be right, you'd have a very good observation there. The total momentum of our system consisting of the marker and the wall has been reduced to zero because it was an open system, okay? If we want it to be a closed system, we need to consider all the participants in the system. The Earth is participating in this system. So the momentum of this marker was transferred to the wall, and if the momentum of the marker was reduced to zero, the momentum of the Earth has increased by the same amount. So momentum was conserved. The momentum of the marker was transferred to the Earth. And the reason we don't usually consider that is because the Earth has thousands upon thousands of kilograms of mass. So whatever momentum that my marker imparted onto the Earth is negligible, okay? But momentum was indeed conserved because it was transferred, all right? Now, let's consider a problem here. Now, this problem is going to introduce us to the concept of momentum in 2 dimensions, okay? So, let me give you an example. Let's say I have a ball here of mass m, and I have a ball here of mass 2m. Let's say that this ball is stationary, its velocity is 0, and this ball is moving with a velocity of 5 meters per second, okay? Let's say that this ball collides with the second ball at an angle, such that after the collision, I'm going to call this ball 2 and this ball 1. Ball 2 is ejected towards the top of the page with a velocity, and ball 1 is ejected towards the bottom of the page with some velocity. Okay? You can see this when you play billiards. If you use the cue, I think it's called a cue, the stick, when you hit one of the balls with the cue, and the ball that you hits a stationary ball at an angle, the 2 balls deflect across each other, each with their own momentum in opposing directions, okay? So in order to analyze this problem, let's say that we're looking for the velocity of ball 1 after the collision, okay? We would also be given the angle theta above and below the horizontal here. Let's call this theta 2, this theta 1 for ball 1 and ball 2, okay? So let's call theta 1 40 degrees, or no, let's call it 20 degrees, and let's call theta 2 40 degrees. All right, so let's analyze our problem. Let's first calculate our initial momentum, okay? Because we're going to want to apply the law of conservation of momentum here. The initial momentum is the combined momentum of these 2 blocks or spheres before the collision. So P equals the sum of all the m's and the v's. This guy has a 0 velocity, so the contribution of momentum from ball 2 is 0, which therefore leaves 2m times the velocity of 5 meters per second. That's going to be our initial velocity, 10m, equals the total momentum, equals the final momentum. Okay? So notice that this is the momentum in the x direction, so it's a vector, okay? Let's consider the momentum in the y direction. Is either of these balls moving in the y direction? No. So our net velocity initially, our net momentum initially in the y direction is 0, which must equal our final momentum in the y direction, okay? So the momentum upward from the top ball must be equal in magnitude to the momentum downward of the bottom ball, all right? So let's bring this problem further over here, okay? We know that when we sum up all of the y components of momentum, that must equal 0. So how do we get the y component of momentum in this case? It's the momentum of ball 1 multiplied by the sine of 20 degrees, sine of theta 1, and if we add that to the momentum of ball 2 times the sine of theta 2, that should equal 0, okay? So let's bring out our calculators, and if we do sine of 20 degrees, that's momentum 1 times 0.34 plus momentum 2 times, which is going to be sine of 40, 0.64 equals 0. Okay, therefore we can say P1 times 0.34 equals P2 times 0.64. Of course, they're magnitudes. Okay, so P1 equals P2, and we can divide by both sides by 0.34, and that gives us 1.88. Okay, so we know that the momentum of ball 1 must be 1.88 times the momentum of ball 2. Now let's solve our equation in the x direction. We know that the momentum of ball 1 times its x component, which is going to be cosine theta 1, plus the momentum of ball 2 times its x component, cosine theta 2, must equal our initial momentum in the x direction of 10m. Okay? So since we're given our angles, let's do cosine of 20 degrees, P1 times 0.94, plus P2 cosine of 40, 0.77 equals 10m. And now we have an equation that gives us P1 in terms of P2. Okay, so we're going to replace P1. P2 times 1.88, we're going to pull that in from here. Again, times 0.94 plus P2 times 0.77 equals 10m. Okay, so let's do the math on this. We got 1.88 times 0.94. That gives us P2 times 1.767 plus P2 times 0.77 equals 10m. We're going to add those two together, plus 0.77. So P2 times 2.53 equals 10m. Divide 10m by 2.53. Get that our momentum of the second ball is 3.95 m. Okay? And now that we've calculated the momentum of the second ball, we can calculate the momentum of the first ball, of course, given by this equation. P1 equals P2 times 1.88. We get 3.95 times 1.88, so that P1 equals 7.42 m. Now we have our final answer. We got the final momentum of block 1 and the final momentum of block 2. Okay? And from those, we can calculate velocity. So for momentum 1, it's going to be 7.42. No, that's momentum 2. Excuse me. This is momentum 1. 7.42 m equals 2m times the velocity of the sphere. So we divide both sides by 2m, and we get that the velocity is 3.7 meters per second for ball 1. Okay, and you would do the same if you wanted to find the velocity for ball 2. Okay, now from there, we have another way of analyzing conservation of momentum. Okay, so if you want to calculate the total momentum of the system, you could sum up all the individual momentums of the particles or participants in the system, or you could calculate the velocity of the center of mass of the system. Okay, now a lot of you may remember center of mass from Unit 2, where we had all those calculus equations and it was probably a nightmare for everyone. But here, it's the same thing all over again. Okay, so velocity of the center of mass is just the sum of the masses of all the individual components times the velocities of all the individual components divided by the total mass. Okay, so here we won't be introducing all that calculus, because in the momentum we are only going to be considering systems of a finite number of particles. Okay, so here was an example of a system with a finite number of particles, just 2 participants, 2 collisions. Okay, so in this collision, let's try and calculate the velocity of the center of mass. So we have 2m times 5 plus m times 0 divided by the total mass of the system, 3m, 2m plus m, which is going to equal 10m over 3m. So the velocity of the center of mass is 10 over 3 meters per second. So now that we have the velocity of the center of mass of the system, we can say that the total momentum of the system is equal to the total mass of the system multiplied by the velocity of the center of mass. Okay? When you have that, you know that since you know that the total momentum of the system cannot change, and the total mass of the system cannot change, you know that the velocity of the center of mass cannot change. Okay? So if we calculate the velocity of the center of mass both before and after the collision, those should be equal. Okay? The final topic we're going to cover here in the momentum unit is the topic of elasticity. Okay? And elasticity is simply defining the character or the characteristics of collisions or interactions. In the AP Physics course, we're only going to consider 2 scenarios. A collision that is perfectly elastic and a collision that is perfectly inelastic, when in reality collisions exist on a continuum or a gradation between the 2 extremes. So a perfectly elastic collision is when conservation of momentum holds. A perfectly inelastic collision is when conservation of momentum holds. So the important thing there is that the law of conservation of momentum holds no matter what problem you're solving. So you should always apply conservation of momentum. Okay? In a perfectly elastic collision, the total amount of mechanical energy is conserved. In an inelastic collision, the total amount of mechanical energy is not conserved. Okay? So recall what we said about mechanical energy. If we have a change in mechanical energy, it means that some of our energy was converted to either heat or sound. Okay? So in an elastic collision, you can say that the initial momentum equals final momentum, and that the initial kinetic energy equals the final kinetic energy. But in an inelastic collision, you can only say that the initial momentum equals final momentum, because mechanical energy is not conserved. However, in a perfectly inelastic collision, the 2 participants, the 2 particles, the 2 objects, stick together. That is a characteristic of a perfectly inelastic collision. I have one ball comes and collides with another ball, and after the collision, they move together, attached. That's a perfectly inelastic collision. So in a perfectly inelastic collision, you can say that the final velocity of participant 1 equals the final velocity of participant 2 because they stick together. So that's just another set of tools, another set of equations that you can use in your belt whenever you're solving conservation of momentum problems, whenever you're solving collision problems. Another interesting type of problem that I want to expose you to before we sign off is the concept of the explosion. Okay? If I have a brick right here, and in the center there is an explosive, right now, when it's resting, the total momentum of the system is 0. It's not moving, or I should write mp sub tot. Total momentum of the system is 0. Okay, therefore, after the explosion, the portion of the mass that is moving in this direction must have the exact same momentum as the portion of the mass that is moving in that direction. Okay? That's why I often use the word interaction instead of the word collision, because the law of conservation of momentum holds for any interaction. Thank you guys for watching.